You often hear people talking about how hard Vulkan is and how it takes so much code just to get to a triangle. And while that's true, there is a lot of code and Vulkan can be hard. I think the hardest part about learning Vulkan is the lack of clear and easy to follow tutorials and code samples. This was my motive for putting together this hefty video. Everything you need to go from zero to your first triangle in one easy to follow lesson, with a focus on modern Vulkan features. Many tutorials, even recent ones, still use Vulkan 1.0 era features, which can nowadays be replaced by their new and improved counterparts. There are also too many concepts introduced at once, far more than is needed to put pixels on the screen, which can leave you with many points of failure when you're just starting out. Even recent learning materials aren't without their issues. I recently went through the How to Vulkan 2006 guide, and though it's quite good, it does leave out some sections that force me to poke through the source code, which I could only make sense of because I've already worked with Vulkan. I personally have a very hard time learning from code like this. Everything is just plopped inside of main, there's nothing to break up the complexity or help demonstrate the various phases of Vulkan initialization and rendering. The comments that are there might as well just be line breaks, as they don't tell me anything. And speaking of line breaks, there aren't even those in this file, which makes me really struggle to want to read this. I do truly appreciate the work that gets put into these materials, but can we agree that educational materials need to be a little more beginner friendly? With that said, I'm going to take a stab at presenting an absolute minimal and modern Vulkan example that beginners can use to try and get to the holy triangle with less pain and confusion than what has been offered until now. We'll do this by only focusing on the features we need to achieve this goal. As we add more features like model loading, texturing, lighting, materials, etc., I'll introduce the Vulkan features that we need and that are best suited for the task at hand. Essentially, I'd like to tackle specific milestones with each video, not introducing just particular parts of the API. And speaking of the API, the Chronos group has put a lot of effort into improving Vulkan since its initial release. This is why anybody starting today should focus on using the core extensions on offer with the latest version of Vulkan, that being 1.4 at the time of recording. Many pain points have been addressed with additions to the API or improvements over existing API. We'll address these as we move forward and look at what the alternative was in the 1.0 era of Vulkan. This will make learning much easier since the areas of Vulkan that required the most boilerplate code or caused the most confusion have been the primary targets of improvement. Also, don't worry about whether you should use the latest features, since by the time you actually get to a place where you're shipping a game and having to worry about device support, you'll likely already have it. Of course, you can always provide ways of supporting old devices, which in practice usually results in an OpenGL ES renderer or simply code paths utilizing widely supported legacy features. But you don't have to worry about that today because you just need to worry about learning and making progress. So let's get to it. To get the Vulkan SDK, head over to the LunarG website, which provides SDKs for Windows, macOS, and Linux. The macOS version of Vulkan is actually a translation layer called Molten VK, which is a wrapper around Apple's native graphics API, Metal. Keep this in mind if you're on macOS, as certain features may be lacking. One thing I'd like to point out, be sure to install shader toolchain debug symbols. I found out the hard way they're needed later when we look at compiling shaders at runtime. Without them, you won't be able to link your debug application against the shader compiler library. Once you've installed the SDK, then you can pull in the Vulkan headers and get started. Let's quickly have a look at the CMake list.txt file for this project. We'll be using SDL3 for the windowing and platform specifics, and the Vulkan library, of course, provided by the SDK that we just installed. The SDK also lets you install Volk, which we'll use to load the Vulkan function pointers later on, so that we can actually call functions, as well as the Vulkan memory allocator library, VMA, which is basically standard nowadays for streamlining memory allocations. I'm also enabling the latest C++ for my MSVC toolchain and telling CMake that I'd like to link to the aforementioned libraries as well. Taking a look at the main.cpp file, we can see that I've placed all of the code inside of a class called application. This isn't a prescription on application architecture. I've just chosen the simplest way of encapsulating things and breaking up the process in order to avoid having a bunch of global variables and functions. After creating an instance of the application class, we call the Initialize method where all of the setup work actually happens. The first thing we do is initialize SDL3 for video. We do this in order to be able to create a Vulkan-capable window. We call SDL init subsystem and pass the SDL init video flag. If everything goes well with the SDL initialization, we go on to create a window and we pass the SDL window Vulkan to the list of window flags to ensure that we can later create a Vulkan-capable window surface. We'll need this in order to create the swap chain later. This is a chain of images that we get from the OS that we can draw on frame over frame. After ensuring that the window was created successfully, we can move on to actually initializing Vulkan by calling our Initialize Vulkan method. Moving into the Initialize Vulkan method, the first call is to the Vulkan create instance method. And in there, the first thing we do is initialize Volk. As mentioned earlier, Volk is the library that's going to load the Vulkan function pointers from our Vulkan instance later on. This here is the first Vulkan structure we'll be using in our setup, and it illustrates a common pattern used throughout the Vulkan API. You create a struct, which always starts with the letters VK, and the first member you always fill is the S-type member field. This tells Vulkan what the type of the struct we're passing is. You might think this is redundant, but Vulkan uses this identifier internally in order to be able to cast our structure to a generic type and then back to its concrete type at a different time. Vulkan is a C API, so this is required in order for Vulkan to be extensible, as we'll see later on when we use another field called pNext. In the case of this struct, VK application info, we provide the type of the struct, the name of the application we're creating, and the Vulkan version that we're targeting, which I've declared as a constant in the header for this class as Vulkan version 1.4. With the appinfo struct prepared, we now move on to creating a list of Vulkan extensions we'll be using with our Vulkan instance. Since SDL is taking care of creating our window, we'll ask it what extensions it needs in order to create the Vulkan surface. The SDL Vulkan get instance extensions function, that's a mouthful, will tell us exactly that. This function takes a pointer to an integer, which will be filled with the size of the returned array, and it returns an array of C strings representing the list of extensions SDL will require to create the Vulkan surface. Once we have SDL's extension list, we can create the final list that we'll be providing to Vulkan when we ask it to create the instance object. I'm also adding the VkExt Debug Utils extension, which is declared in the Vulkan headers under the VkExt Debug Utils extension name constant. This extension lets us provide the Vulkan instance with a callback function, which can receive messages from the Vulkan driver, letting us know about API misuse or potential performance issues, and is part of the overall validations layer feature of Vulkan that we'll enable. Every Vulkan developer should enable this during development, whether they're a beginner or an expert. We'll look at enabling layers in a minute. Now it's just a matter of iterating through the extensions SDL asked for and pushing them into the requested extensions vector. Before we move on though, let's quickly take a look at what's actually in there. First, we see the VkExt Debug Utils, which I described a minute ago for the debug callback, which is followed by VkKHR Surface, which is the generic Vulkan surface extension that we'll need to create a surface. There's also VkKHR Win32 Surface, which is needed for this particular platform, Windows. macOS and Linux users will see a different extension. And both of these last two extensions were returned by SDL further up and will be required when we create the Vulkan surface shortly. As mentioned, we'll need to tell Vulkan which layers we want to enable for the runtime of our application. In this case, all I'm asking for is the validation layers to be enabled, which is done by passing the VkLayerChronos validation identifier to the requested layers vector that we'll be passing on to Vulkan shortly. Moving on from there, we create another VK struct that we'll provide with our instance creation, letting Vulkan know what the debug callback function is we want it to call, as well as what type of messages we're interested in and the severity levels we care about. The callback function has a very specific signature, as you can see on screen, and is usually just a plain old C function that we provide a pointer to. In my case, I've defined it as a static method in the application class, which you can also provide a pointer to the same way. This can't be a regular class instance method, as Vulkan won't know what object to call it on. Take note that in the method definition, I'm also able to filter out severity levels from there with a simple equality check. In this case, I only care about message severity warning and higher. Okay, we have everything we need to create the Vulkan instance. In order to do that, we create an instance of another struct named VkInstanceCreateInfo and provide the information Vulkan needs to create the instance. This includes the appInfo struct detailing our app name and Vulkan version, the instance level extensions we'll be requesting, the layers we wish to enable, and the debug callback information we just looked at. When people say it takes 1,000 lines to draw a triangle, this is one of the reasons for it. There's nothing overly terrible or difficult about what we're doing. It's just a matter of providing lots of information to Vulkan so that it can later make informed decisions about how to best execute the things that we tell it to execute. Looking at the pNext field being set on the struct brings up an important note. You'll recall I mentioned earlier that the S-type field on the struct is used by Vulkan for extensibility support. An example of this is right here, where we set the pNext field to point to a VkDebug messenger create_info ext struct. pNext is a void pointer and another standard field you'll see often. It allows us to essentially create our Vulkan structures into linked lists, each one pointing to the next. When you call methods from the Vulkan API, in many cases Vulkan will follow each pNext pointer, cast it internally to a base generic type, and look at its S-type member. This way, it has a generic way of viewing the S-type fields on any structs provided. Using the structure type field, it can then create a concrete object of that specific type and perform the appropriate work. This is why it's important to always set the structure type in Vulkan. And while we're at it, it's important to remember to always memset your structs to 0, or just use an appropriate construction method. In C++, using the braced initialization I'm using always initializes the fields. This way, there's no risk of initializing a field with garbage data from memory and accidentally setting off strange behavior. Another common pattern is the way we're passing the lists of extensions and layers. You'll always see pairs of fields where one states the number of things you wish to pass and another points to the memory holding those things. Now that you understand those basics, let's call our first Vulkan function, VkCreateInstance. This function will take our instance create info struct, a pointer to an allocator callback, which we don't need and will pass null pointer, and finally a pointer to the VkInstance variable where we wish to receive the handle to our newly created Vulkan instance. It's good practice to also check if the result of our function calls is VkSuccess, so that if something goes wrong, we can end early and take appropriate measures. Some functions return other details, as we'll see later, so it's important to understand what the functions return, as we'll see later when we work with our swap chain. And just for reference, all Vulkan object handles and other data are stored in the application class instance we're working with, such as the VkInstance handle we're receiving our Vulkan instance into. With the VkInstance created, we're ready to ask Volk to get us the addresses to all of the Vulkan instance level functions. These will be all of the functions that we'll use to interact with Vulkan going forward. Without this step, a call to any Vk function will result in a crash. So we call Volk load instance, pass in the Vulkan instance we just created, and it takes care of the rest for us. And of course, if you create or initialize something, you need to remember to also free it when you're done. Let's look at the portion of the shutdown function that is called at the end of the program corresponding to the Vulkan instance creation process we just completed. These function calls are at the very bottom of the shutdown function and are the very last thing to get cleaned up when the application ends, just like how they were the very first thing that we initialized when the application started. First, we call VkDestroyInstance and tell Vulkan we're finished with the Vk instance. Then we call VolkFinalize to clean up any resources it may have used. Then we can destroy the window that we created with SDL by calling SDLDestroyWindow. And finally, we can shut down SDL as a whole by calling SDLQuit. That's all there is to it. We'll be adding more to this shutdown function as we go along, but for now, this is all we need to clean up after ourselves. So we have a Vulkan capable window created, we've initialized the Vk instance, and can start calling Vulkan functions that we acquired through Volk. Next up, we create the VkSurface object, which we're going to use to create our swap chain shortly. For now, creating the surface object itself is a simple matter of calling SDL Vulkan create surface, passing in the window pointer and the handle to the Vk instance object. We continue to pass null pointer to all the allocation callbacks, and we provide a pointer to a VkSurface variable in the application instance where we're actually going to receive the surface handle. If we created the window correctly and requested the appropriate Vulkan instance extensions, this function should return true and we can move forward. We've worked towards setting up a window and an appropriate surface that we can eventually use for drawing, but we still haven't told Vulkan what GPU we're going to be using to actually do so. In Vulkan, your GPU is represented by a physical device object. And even if you have a single GPU in your system, you still need to tell Vulkan that you intend to use it. Let's take a look at the find physical device method. This is one of those areas where tutorials spend far too much time up front, iterating the GPUs, checking capabilities, assigning scores to them, and trying to figure out which GPU to use. Having a solid algorithm for detecting the appropriate GPU is important, but honestly, it's not that important when you're just starting out and want to see some colors on the screen. As far as I'm concerned, I would prefer beginners just pick the first GPU in their system and move on. But I can't just leave you with that, so I'll take a little time and show you how to enumerate the physical devices to pick one. It's also not a bad bit of code to learn from anyway, as we'll see another calling pattern that comes up a lot with Vulkan as you ask it to enumerate things or give you listings of some sort. What you do is create an integer that will hold the number of things Vulkan is giving back to you. In this instance, we're asking Vulkan to give us a list of the physical devices in our system by calling VkEnumerate You'll notice that you're expected to do the call twice. The first time you call it using the Vulkan instance handle, a pointer to the integer that will receive the count value, and a null pointer for the last parameter. This is where you'd otherwise pass the pointer to a memory buffer of the correct size to receive the items Vulkan is giving you. When you pass null pointer for the buffer address, Vulkan only gives you the count of the items and doesn't try to give you any data. Once you have the count, you can allocate a buffer to hold that exact number of items and then call the function again so that you can actually get them. This time, we use the vectors data method to get the address of the memory we allocated, and Vulkan will have a place to write out the VK physical device handles for us. With our list of physical devices, let's look at a simple way to pick one for now. We create a VK physical device variable and initialize it to null pointer. This is the variable we'll return at the end of the method. Next, we check if we actually got back any devices from Vulkan. If this value is 0, then the function will obviously skip everything and return the null pointer that we assigned previously. The calling function will see that and report the error. Most likely, you'll have at least one physical device in your system, or two if you're on a gaming laptop or a workstation. First thing we do is initialize the chosen physical device to the first item in the list. Then we can loop through the list of physical devices and inspect them. We create an instance of a VK physical device properties struct, which we'll ask Vulkan to fill with the details about the current physical device in the loop. We call VkGetPhysicalDevice properties, pass the handle to the current physical device, and the pointer to the struct that we created above. Once we have the properties, we can check the device type field to see if it's a discrete GPU, using the VkPhysicalDeviceType discrete GPU constant, which means our loop here is looking for a dedicated GPU over an integrated one. If we find a discrete GPU, we assign the handle to our result variable, break out of the loop, and return. If we don't find a discrete GPU, then this method will just end up returning the first GPU in the list. Once this method returns to us a physical device, it's time to take a look at where our commands actually go when we tell our GPU to do work. Modern graphics cards are packed with both generalized and specialized hardware. We have engines for rendering, high-speed computation, and dedicated DMA engines for moving data between system and video memory without stalling our graphics pipeline. The way Vulkan abstracts and exposes this hardware is through the use of queue families. You can think of these as various types of pipes flowing into the GPU for work delivery, and from those families, we can create VkQ objects that represent the actual pipes that are based on those families that we can actually pump data into to send into the GPU. Examples of queue families are graphics. This is where we submit render commands for executing our various graphics shaders. Compute, which we use for compute shaders and non-graphical applications. And transfer, which are specialized hardware for directly accessing system memory. This allows for seamless loading of assets into VRAM in order to minimize frame rate disruption. There are also video decode and encode queue families and a few more specialized ones that we won't be looking at yet. In order to get our triangle to the screen though, we need to be able to do the following things. 1. Tell the GPU to draw 3 vertices so that it can execute a graphics pipeline to process and shade the appropriate pixels, or more correctly, fragments. Then we need to write those fragments into an OS-provided set of images called the Swapchain, which we'll be creating soon. And finally, we need to have the image presented after we're finished drawing on it in real time. The Vulkan specification guarantees that if you have a graphics family queue, you have implicit support for graphical and memory transfer operations, which is why to start, the only thing we'll care about is the graphics queue family, and virtually every single GPU will have this one. In fact, for our example, we aren't even transferring any model or image data such as vertices and textures to the GPU, so all we'll really need are the graphics capabilities. In fact, we won't even care about dedicated transfer queues until a further video where we'll focus on loading game assets asynchronously using the dedicated DMA engine in an optimized way. Until then, a graphics queue is more than enough to load and render models and textures without overcomplicating matters and prematurely optimizing. To find our graphics queue, we'll first ask Vulkan to give us a list of the various queue families available to our physical device, which also gives us some capability information about them. This is done by calling VkGetPhysicalDevice QFamilyProperties2. We call this function multiple times as demonstrated in the previous section in order to correctly size and fill a buffer with the appropriate structures. If you're curious about the number 2 suffix at the end of some of these functions and structures, this is how the API has added updated versions of legacy functions and structures without causing breaking changes to the existing legacy code in use today. Once Vulkan has given us the list of queue families available for the GPU, we iterate over each one and check if it's right for us. I previously mentioned that after we're finished drawing our triangle, we'll need to be able to present the image, of course, to the window. This is done by communicating with the presentation engine and the Windows system interface to ensure that we can reach a level of synchronization between our renderer and the OS subsystem responsible for actually displaying our window to the screen. We'll discuss that synchronization shortly, but for now, we need to check if our queue family has support for presentation, and more specifically, if it has surface support. The queue family which we'll use for graphics is usually universal and will almost certainly have presentation support, though we'll be good Vulkan devs and we'll make sure to check for it explicitly. First, we'll create a for loop in order to create an index variable that we can use to index into the list of properties objects that Vulkan gave us. And for each index, we call VkGetPhysicalDeviceSurfaceSupportKHR, passing in our physical device handle, the current queue family index, the VkSurface object we previously created, and a pointer to our Boolean variable that we declared above to receive the result. This will tell us if the queue family at the given index will have support for presentation. Next, we grab the current properties object by indexing into the list that Vulkan provided, and we check if the current queue family has the VkQGraphics bit set in the QFlags field, which is exposed by the queue family properties object. And we use a bitwise AND to check for that bit. Of course, we're also checking if the result is true for the presentation support we discussed. And if both of these conditions are true, we keep track of the queue family index using a member field in the application class. Then we can just break out of the loop and function by returning true. We'll need this index shortly to create the queue object we'll be using to submit render commands to the GPU. If everything goes well and we get our graphics queue index, we get a true result here and can move on to the most important object of our application. And this is the logical device, or more accurately, the VkDevice handle. Modern GPUs are powerful devices that are designed to be used by multiple applications at once. If you run a game and play a video at the same time, the same GPU will be rendering frames in your game, while at the same time it's decoding video frames in your browser. This is handled by allowing various instances of the GPU to operate concurrently, sharing and prioritizing hardware resources. To use an analogy, if you think of the physical device as a class type in your application, you can think of the VkDevice as an instance of that class, representing an actual instantiation and usage of that class. You never submit work directly to the physical device, you access the GPU via a logical device handle, provided to us as a point of access for GPU resources. Let's see how we can get ourselves one of these. Drilling into the createDevice function, we see that it takes a VkPhysicalDevice as a parameter, and I've done this just to reinforce the idea that a VkDevice is created based on a VkPhysicalDevice. We start off the process by creating a series of structures that will hold the supported features of our selected physical device. These structures will tell us what Vulkan features are supported, and each struct represents a different version of Vulkan. As you can see, each one is numbered. 14 is Vulkan 1.4, 13 is 1.3, and so on. The bottom structure represents Vulkan 1.1, and we're using the to suffix variant in order to have access to the pnext fields. As we discussed, this pointer lets us link structures together to form a linked list that Vulkan can traverse until it finds a null next pointer. In our case, that'll be the Vulkan 1.4 feature structure. These structures contain a series of Boolean fields that will be populated by Vulkan when we call VkGetPhysicalDeviceFeatures2 and pass the first structure in the chain. Once we have our supported features, we check to make sure that each feature we're actually interested in is available to our graphics hardware and driver. It's important to remember that different operating systems have different driver quality and Vulkan support, so it's crucial to ensure a feature is supported before you assume you can use it. If all of the features we're interested in are supported, we move on to the next section, where we once again produce another chain of these feature structures, except this time we'll be the one setting the appropriate feature fields to true. We'll be using this chain in a minute to tell Vulkan that we want these features to be enabled when we create the VkDevice object. Remember, you should always enable only the features you're actually planning on using, which means making sure to create the second chain of structs and explicitly setting the appropriate Boolean fields. It might be enticing to get the supported features using the first chain of structs and just pass that along when we create the device, but this is bad practice. This way you would enable everything, which will cause the driver to make certain decisions and assumptions that could impact your application's performance, and you could certainly end up paying for something that you're not using at all. You should also be aware of which parts of the API you are using and which extensions it belongs to. This will only make you more informed and able to make better decisions. You could eventually provide wider support by conditionally enabling certain features for different hardware configurations. Like I said earlier though, at this stage, use the non-vendor specific features that will make your life easier and let you make progress as rapidly as possible. And basically everything we're using today is already part of the official Vulkan feature set. Once we've set up our requested features, we need to prepare another structure to tell Vulkan that we'll need a queue so that we can actually submit work to the GPU using our device. We previously found a particular queue family that supports graphics and presentation features and kept track of its index in the application class member field. We prepare a VkDevice queue create info structure and populate it with the queue family index, the number of queue objects we'd like to create, and a pointer to the list of queue priorities corresponding to each queue object that we're asking to create. In this case, it's just a single queue, so it's a vector of one element with a priority of 1.0, which is standard. It's quite rare that you'd want multiple graphics queues, as there really won't be any benefits for most applications. And if you do ask for more queues, the GPU might actually allocate its resources more thinly in anticipation for multiple queues and actually harm your performance. Even if you're looking to create a modern multi-threaded renderer, you don't achieve that with multiple queues, but rather by recording multiple command buffers concurrently in multiple threads and then submitting those command buffers into a single queue. We're almost ready to create the VkDevice object. We'll just need another struct of VkDevice create info that wraps everything up together. We set the required sType field and the pnext field to point to the first feature structure of our requested features chain. We specify how many VkDevice queue create info structures we're passing, which in our case is just a single graphics queue, and that's followed by the count and list of extensions that we're enabling at the device level. Here, we only have the VkKHR Swapchain extension, which is a companion to the surface extension we enabled at the instance level. We'll need this in order to interact with the always provided swapchain using our VkDevice. And I'm also setting the p-enabled features field here to null pointer explicitly to stress that in modern Vulkan, you provide a chain of structs for the enabled features as we've done above, and you don't use this field to pass that chain. Keep this in mind, as trying to pass this chain using this field will only result in a compile error as the types don't even match. Finally, we call VkCreateDevice, provide the physical device handle, a pointer to the struct we just created, null pointer for the allocator callback, and a pointer to a VkDevice handle variable we declared in the application class. If this returns VkSuccess, we'll have ourselves a VkDevice object that we can finally start using to access GPU resources. And the first of those resources will be the VkQ object that we asked Vulkan to create for us with the device. This simply involves calling VkGetDeviceQ with our new device handle, the Q family index we're interested in, and the index of the Q which we just created, which is 0 since we only created a single Q. We also provide a pointer to a VkQ variable that'll receive the Q handle. If everything went well, we'll have our device handle, our Q handle, and we're ready to move on. If you're enjoying this video so far and want more of this content, please consider liking and subscribing to the channel. This really helps with the algorithm and makes all the hours of recording and editing that much more worth it. You can also support me using my Ko-fi link, which is in the description. Now let's get back to the lesson. I've mentioned GPU resources multiple times now, but when we talk about GPU resources, we're most commonly referring to images that hold texture data and buffers to hold vertex, material, or virtually any other scene data. This has historically been a pain point for beginners, as even simple allocations required multiple steps, such as describing the buffer size and usage parameters, creating the buffer and getting back a VkBuffer handle, using that buffer to generate a memory requirement structure, enumerating and picking an appropriate memory type from the physical device, and once you have the buffer requirements, creating a memory allocation request structure to actually allocate the memory and get back a VkDevice memory handle. And this often requires quite a bit of code just for simple memory allocations. Nowadays, it's highly recommended to use a library called VMA, which stands for Vulkan Memory Allocator. The library is used by major companies and has become a standard tool for Vulkan developers of all levels, and is included with the Vulkan SDK. It aims to provide a huge reduction in boilerplate code by automatically setting up most of the commonly used fields, enumerating and using the appropriate memory type, and managing the memory allocations for us. This doesn't mean we can't fine-tune memory use further, it simply offers a reduction in complexity and code size required for memory allocation. Setting up VMA is actually very simple, as we'll see in the Initialize VMA method. First, we create an empty struct of type VMA Vulkan functions and empty initialize it. Then we create another structure of type VMA Allocator create info, where we provide VMA some info about our current setup and intentions. Most of the fields like physical device, Vulkan instance, and Vulkan version are self-explanatory. The ones to note though are the flags field, where we're currently telling VMA that we intend to use the buffered device address features of modern Vulkan, which will let us access VRAM directly in shaders using a pointer. We won't need it for this first tutorial, but I'm enabling it now as we'll use it in the next video when we load GLTF scenes into our application. The other notable field is the p-Vulkan functions field, which we're setting to the address of the currently empty Vulkan function struct we declared above. With the two structs now linked up, we can call VMA import Vulkan functions from Volk, as we've already set up Volk at the beginning of our application. This will populate the VMA Vulkan function structure with all of the function pointers VMA will need to manage memory for us. Now it's just a matter of calling VMA create allocator, passing in a pointer to the VMA alloc info struct, as well as a pointer to a VMA allocator member field declared in the class. If this function returns VkSuccess, we're done here and we have an allocator that we're able to use going forward. Before moving on to the next step, let's revisit the shutdown method and ensure the new objects we've created have corresponding code blocks to clean them up. The order is important here, since if you delete the VkDevice before deleting any allocated resources for it, Vulkan will complain. This is why we first call VMA destroy allocator and pass in the VMA allocator handle, though this will only destroy the allocator. We'll look at how to free VMA allocated resources shortly. Then we call vk destroy surface khr, passing in the vk instance and the vk surface khr handles, as well as null pointer for the allocator callback. Then we can finally call VkDestroyDevice with the device handle and null for the callback, which will destroy the VkDevice. As we've worked through the Vulkan initialization, the term Swapchain has come up a number of times, but we still haven't talked about what it really is and how it's designed to be used. To begin to understand what the Swapchain represents, recall that we created our window with Vulkan support enabled in order to create a Vulkan surface object. What we did was set up the groundwork to acquire a set of operating system owned images that will be the render targets of our Fragment shader. Since the operating system owns the window and everything inside it, we need to treat those images as if they have been loaned to us and could be taken away at any time. We ask the operating system for the images, then request one each frame, and use the GPU to ensure that it's prepared so that it can be drawn on. Once we perform our rendering operations, we use the GPU again to ensure that its data layout is appropriate for presentation, and then hand it back to the presentation engine for display. When we look at the rendering method, you'll have a much better understanding of how this is done through the use of Semaphores to synchronize our renderer with the underlying presentation system. We'll also learn what to do when the swapchain becomes invalid due to common events like resizing, minimizing, or shifting the window from one screen to another. What this means is that the swapchain, its images, and any other image used as a render attachment need to be recreated to reflect the new window dimensions. The createSwapchain method receives the resolution via the width and height parameters and immediately stores them in the application instance as the new swapchain size. We differentiate between the regular window dimensions and the swapchain dimensions because the events that invalidate the swapchain can occur at any time. And it's important that we don't use the new window dimensions during any swapchain related operations until we've had a chance to recreate the swapchain with the new size. The first order of business is to get some information about the surface, which will dictate how large the image swapchain is going to be. We create an empty struct of type VkSurfaceCapabilitiesKHR and pass it as a pointer to VkGetPhysicalDeviceSurfaceCapabilitiesKHR, which also requires our physical device and the surface object. Once we have our surface capabilities, we can make an informed decision on how many images we're asking for. We first initialize an integer for our requested image count using the larger value between 2, which is the number of images that we want, and the minimum number of images as dictated by the capabilities object. If Vulkan states that we can ask for a minimum of 3 images, we want to make sure that we're not under that threshold, as that'll cause an error and we won't get a swapchain. Unlike the minimum number of images, the maximum number can be 0, which states that we can ask for an unlimited number of them. Though there's a memory limit you could hit here, and it's certainly not a good idea to ask for too many. So we make sure that if that value is not 0 and there is a limit, we don't accidentally go over it by taking the smaller of these two values, our current desired image count and the maximum as dictated by the capabilities. Once we know how many images we want, we can create a struct of type VkSwapchainCreateInfo which will give Vulkan everything it needs to know to create our swapchain. We need to provide the following fields: the struct type as usual, the handle to our existing surface object, the minimum number of images that we're interested in, our desired swapchain image format, and I'll later show you how we actually ensure that it's supported. We set the swapchain color space to sRGB, which is universally used and will ensure colors are reproduced correctly on our displays. We also need to set the swapchain extent, which is another way of saying the dimensions of the swapchain images. This field states that each swapchain image should be an array of 1 images, which really just means a single image. Next, we tell Vulkan how we intend to use the swapchain images, and since all we need to do is draw on them, the VkImageUsageColorAttachment bit is the only one we need to set. It states that we'll be attaching the images as our render target later when we begin rendering. The pre-transform field tells the OS how to orient the image. we're using the current transform value of our surface capabilities to ensure that if the users have rotated their monitors and there is an existing rotation in place, we account for it. In most cases, this will have a value of VK surface transform identity bit KHR, as in identity matrix, or just simply no rotation or transformation. The composite alpha field tells the window compositor to ensure our window is fully opaque, and this is because we can actually make our surface transparent by drawing colors to our swap chain with alpha values less than 1. And finally, we need to select the presentation mode. This refers to how the presentation engine chooses which images we should draw on and the timing at which to display them. We're going with VK present mode FIFO KHR because the standard guarantees that if we can create a surface object, then we can use this presentation mode. And it's also a great one with VSync enabled. It creates a first in, first out queue where images are pushed when we finish rendering on them and submit them for presentation. During a VBlank, the presentation engine picks the image from the front of the queue and displays it, while any new images that we finish rendering on are pushed to the back of the queue. And again, because of the VBlank wait, this mode also enables VSync for us. If we render very quickly and the queue fills up faster than the display can present, we can get a stall on the CPU until a queue slot is available, which in essence throttles our renderer. The next mode that's available is the VK present mode mailbox KHR, which behaves a lot like the FIFO mode, except if the queue is full, the new image just replaces one of the existing ones in the queue and doesn't cause a stall. Then there's the VK present mode immediate KHR, which just displays the image immediately when it's sent for presentation. But this can cause screen tearing as it doesn't wait for a VBlank, which would essentially be our VSync off mode. And finally, there's a VK present mode FIFO relaxed KHR, which behaves like the regular FIFO mode when the renderer is faster than the refresh rate, but behaves like immediate mode when the renderer can't keep up. So when the renderer does end up submitting an image to the presentation engine, it displays it immediately, which could cause tearing. Let's take a quick detour and go over the Swapchain image format. In order to make sure we don't request an unsupported image format, I've added a block of code in the findPhysicalDevice method, which ensures that the selected physical device and surface combination can actually support the Swapchain color format that we're requesting. This is quite simple, and we've seen this convention before a few times. We call VkGetPhysicalDevice Surface Formats KHR multiple times in order to fill a vector of VK Surface Formats KHR values, which will tell us the supported color formats. Then we just iterate over the list and check if the one we want is included, breaking out of the loop when we do find it. The format I've chosen is VK format B8, G8, R8, A8, sRGB, and is almost universally supported, but if by some chance your GPU and surface combination can't support it, be sure to check which physical device is being chosen, and also review the vector of supported formats that Vulkan returns. And finally, we can call VK create swapchain KHR and pass our device, swapchain create info, null pointer for the allocation callback, and a pointer to a VK swapchain KHR variable where we're going to receive the swapchain handle. If all goes well, we can now retrieve the images from the swapchain so that we have something to work with. We'll store the images in a vector container stored in our class instance. Aside from the images, our swapchain will also have a series of VK image view objects, which will describe how we wish to access the images, as well as a number of VK semaphores, which we'll use to synchronize the presentation engine with our renderer. We retrieve the images by calling VkGetSwapchainImages KHR the usual way. First, getting back the image count so that we can size the vector appropriately, then retrieving the actual images. We need the image count here because when we created the swapchain, we told Vulkan what the minimum number of images that we would like is. But we may get more than that depending on the presentation mode. Once we have the images, we also resize a vector of VK image view objects. Then iterate over the swapchain images and create an image view into each one. For each image in our swapchain images vector, create a VK image view create info structure along with the following fields. The structure type is set to VK structure type image view create info. The image field will take the handle to the current swapchain image for this loop iteration's index. The view type will tell Vulkan that this is a regular 2D image. The format will be the image format we chose for the swapchain. And the sub-resource range lets us dictate which portion of the image we'd like to access. Images can be arrays themselves, and each one can have various MIP levels. The Swapchain images are just single images, so we'll specify a 1 for the MIPMAP level count and a 1 for the array layer count, as well as 0 for the base MIP level and base array layer. These represent the starting indices into the MIP and array lists. Then we can call VkCreateImageView with our device, the pointer to our ImageViewCreateInfo struct, no allocator callback as usual, and a pointer to the VkImageView handle for the current image index. We start each frame by asking the presentation engine for an available Swapchain image, at which point we can begin submitting commands to the GPU. Once all of the submitted commands are complete, we then submit the final image to the presentation engine for display. In order to successfully hand the image off to the presentation engine, we need a way to signal that our rendering work has been completed and that the image is ready for display. We do this with the use of a semaphore, which are used to synchronize operations between different GPU queues. We'll create what's called a binary semaphore that will simply signal to the presentation engine responsible for compositing the image to do so at the right time. We'll tell the GPU to signal a semaphore after it has completed the requested operations, and we'll tell the presentation engine to wait on that same semaphore before attempting to present the image. In order to do this correctly, we create a semaphore corresponding to each Swapchain image. When the presentation engine tells us which image we're allowed to draw on by providing its index, we'll use that same index to pick the appropriate semaphore during rendering. As I showed earlier, we have a vector of VkSemaphore objects in our application class, which will resize to be the same size as the number of images in the Swapchain. With that in place, it's just a matter of iterating over the semaphores and creating a structure of type VkSeMaphoreCreateInfo. Since we're using just the regular binary semaphore, which is either signaled or not signaled, the struct doesn't require anything other than the structure type. Then the semaphore is created by calling VkCreateSemaphore, passing the device, a pointer to the structure above, no callback as usual, and a pointer to the current VkSemaphore object where we'll store the handle. And once our loop finishes, we'll have a semaphore for each image in the Swapchain. Since we're just creating the Swapchain at the moment, we'll look at how the semaphores are actually used once we're inside the render method. When drawing to the Swapchain, we process all of our scene meshes in a sequence, sending draw commands along with mesh and material data to the GPU. The commands can be recorded in a particular order, but there are no guarantees that they'll finish in any particular order. This is because GPUs will process each triangle, vertex, and fragment in parallel, so any order we think we've set by issuing the commands in some particular order will be irrelevant. If an object is drawn in the foreground closer to the viewer, and later a more distant object is drawn at that same screen position, the order of the shading operations can cause fragments of the closer object to become hidden by fragments of the distant object. This is obviously incorrect, and we need to ensure visibility order is maintained regardless of draw order. To solve this, the concept of a depth buffer is introduced, sometimes called a Z-buffer, and it works by storing the fragment depth in a separate image than the one we're outputting color information into. In our example, when we draw the closer object, the color and depth information would be written in the color and depth images, so later when a distant object is drawn at that same position, the render pipeline can check if the depth of the new fragment is further from the viewer than the existing fragments, and simply avoid shading the new fragment altogether. Unlike Swapchain images, which are owned by the operating system, in this case, we need to create a VK image ourselves. Also, unlike the Swapchain images, we only ever need a single depth image for our renderer. When we submit a set of commands to the graphics queue to render a particular frame, we submit them to the graphics queue in bulk. There may be 50 commands submitted at the same time for a given frame, potentially completing out of order from their submission order, but the GPU will complete the entire set of commands first before it begins processing the next set of commands in the queue. This means that the GPU only ever renders a single frame at a time, only ever needing a single depth buffer at a given time. To create a VK image for our depth buffer, we create an instance of a VkImageCreateInfo structure providing the following fields: the structure type, the image type set to a standard 2D image, the depth format, which we'll set to VK format D32S float, representing a depth-only buffer of 32-bit signed floating point values. Eventually, we'll use a different format here to create a buffer that stores both depth and stencil information, but for now, we'll focus on depth only. For the extent field, we'll use the dimensions of the swap chain. We don't need multiple MIP levels for the depth buffer, and we don't need this to be an array of images. We're not multi-sampling the depth buffer, so we'll set the samples field to VK sample count 1 bit. The tiling field tells Vulkan how the bytes representing our image should be arranged in memory. In this case, we'll use VK image tiling optimal, which tells Vulkan to choose a memory arrangement optimal for sampling. We set the usage field to VK image usage depth stencil attachment bit so that the image can be used during both depth or stencil operations. And then we need to specify the initial layout of the image to undefined, letting Vulkan know that we don't care, nor do we want Vulkan to waste any time looking at the memory that is initially allocated. We'll talk a little more about image layouts during rendering. With the image characteristics defined, we now need to allocate memory for the image. In the past, we would have had to create a whole lot of code to create the VK image ourselves, detect memory requirements, allocate the memory, and so on and so forth. But in our case, we'll let the Vulkan memory allocator shine. All we have to do is create an instance of VMA allocation create info, set the flags to VMA allocation create dedicated memory bit, telling VMA that we want a chunk of memory dedicated specifically to our depth buffer and not a piece of a larger allocation, and set the usage field to VMA memory usage auto, which tells VMA to look into our image create info structure and make decisions about where to allocate the memory, GPU or system memory, as well as how that memory is going to be accessed during execution. Next, we call VMA create image, passing our VMA allocator, pointer to the depth image create info structure, the allocation info structure we just created, a pointer to a VK image that will receive the handle to our depth image, and a pointer to a VMA allocation handle that will represent the memory used by the depth image. Just like before, in order for Vulkan to know which portion of the image should be accessed during depth writing and sampling operations, we'll create a view into the image memory that will let us use it as a depth attachment later. We create a VK image view create info structure, setting the image field to our new depth image handle, the view type to VK image view type 2D, the format to VK format D32S float like before, and the sub-resource range telling Vulkan that we want to access only the depth aspect of the image data, which also happens to be the only aspect in our case. And we also tell it that we only have a single MIP level and a single array layer for this image. Once again, we call VK create image view with the device, pointer to the image view create info struct, no callback, and a pointer to a VK image view that will hold the handle. And we now have everything we need to use a depth buffer. We previously discussed the number of different events that could invalidate our swap chain, which would require us to recreate it at the start of a frame. Before we can recreate it though, we need to destroy any existing resources previously allocated for the current swap chain, and only then should we call the create swap chain method with the new dimensions to recreate it. Let's take a look at how we clean up the swap chain and the order in which we do it. First, we'll destroy the image views we created for the swap chain images. Then we'll destroy the semaphores we created for each image. Next, we destroy the swap chain object itself. And anytime we recreate the swap chain, we also need to recreate the depth buffer since they need to be the same dimensions. We start by destroying the depth buffer image view, and then call VMA destroy image to destroy the depth image itself, along with the memory allocated for it. This requires the VMA allocator, the depth VK image handle, and the VMA allocation handle that we stored when we allocated the buffer. The destroy swap chain method we're looking at will not only be called when we recreate the swap chain, we'll also call it inside the shutdown method when we're cleaning up the application at the end of execution. You can place it right above the call to VMA destroy allocator to ensure that any VMA allocations for the swap chain are cleaned up before trying to destroy the allocator itself. Now that we have images that we can render to, let's start creating our graphics pipeline which we'll be using to draw onto the images. Before creating the actual Vulkan pipeline, I'd like to go over how we compile our shaders, which we'll need in order to attach them to our pipeline further on. Vulkan uses a shader format called SPIR-V, which is not something you write by hand, but rather it's an intermediate binary format produced by compiling a shader source such as GLSL. Unlike OpenGL though, where you pass your GLSL source code directly to OpenGL, with Vulkan, we need to compile the shader code ourselves. This could be done by invoking the glslc compiler from the command line, or writing a custom target for our CMake project, which can compile the shaders for us at build time. The approach we're going to take is to use the shaderc compiler at runtime. While having the shaders pre-compiled offers a faster startup for our application, there's a huge benefit to compiling at runtime, as in the future we'll be implementing hot reloading of the shaders, letting us see our code changes reflected immediately without restarting the application. You may recall that when I showed the project CMake list.txt file, one of the components we brought in from the Vulkan SDK was the shaderc combined component, which is the runtime shader compiler we'll be using. We'll first need to include the shaderc compiler header into our source code, and then we can move our eyes down to the create shader module method. It receives the shader file name as well as another parameter of type shaderc shaderkind, which tells the compiler what type of shader we're compiling. It could be a Vertex, Fragment, or another type of shader. Once we enter the body of the function, we first build up the file path by concatenating the folder where the shaders are stored to the file name that was passed in. I like to keep my shaders in my application source tree, so I have to set the working directory for my run configuration in order for my application to find them at runtime. In Visual Studio, you do this with the Debug Properties panel for regular VS solutions, or the Debug and Launch settings for CMake-only projects. Once we have the shader path established, we can load the file from disk and store the source in a string. I've written a read text file helper method, which will read the entire file into a string stream buffer object, and then return it as a regular std string. If the file is successfully read, we move on to the compilation phase. Thanks to shaderc, the process is quite simple. We create an instance of the compiler class, as well as an instance of the compile options class. Here we specify that we're targeting Vulkan, and specifically Vulkan version 1.4. Next, we set the target to SPIR-V 1.6 and the compiler optimization level to performance. With that, we can call the compiler's compile glsl to spv method, passing our source code string, the shader kind we received in the method, the original file name which shaderc can use for reference later, and the compile options. After this method completes, be sure to check the compilation status and also print out any compilation error messages that may exist. If there is an error in our compilation, we just return a null pointer and leave the function. If everything goes well and our shader is successfully compiled down to SPIR-V, we'll have an object of type compilation result containing a buffer of unsigned integers representing the compiled SPIR-V binary data. All that's left is to create the VkShader module object, which will be the handle to the compiled Vulkan shader that we'll be using with our pipeline. This is done by creating an instance of the VkShader module create info structure, setting its type accordingly, and the size of the shader in bytes, which can be calculated by subtracting the beginning iterator from the ending iterator and then multiplying the result by the size of the 32-bit integers that make up each element of the array. The pcode field expects a pointer to the start of the buffer, which can be retrieved by using the results cBegin method. Now we can call VkCreateShader module, passing our VkDevice, a pointer to the VkShader module create info structure, no allocator callback, and the address of the VkShader module variable we declared and initialized to null above. Provided everything goes well, our method will now return the handle to the VkShader module that we can use with our pipeline. With the bulk of the shader work complete, let's take a look at the createShaders method that we're calling during initialization. It calls the createShader module method twice, once to create the Vertex shader and once to create the Fragment shader, Both shader modules are stored in our application class instance in their associated VK shader module fields. Anyone who's worked with an older graphics API will know that they're basically large state machines. The latest versions of OpenGL have tried to move away from this model as much as they can, but at its heart, OpenGL is a stateful API, and the same can be said for DirectX 11 and earlier versions. Vulkan is a much more explicit API than both of those. In fact, Vulkan is even more explicit than its twin, Direct3D 12. Older APIs allow you to easily change rendering state and submit draw commands to the driver, which is actually really nice when you're learning graphics programming and would like to prototype and iterate quickly. But this ease comes with a decent amount of driver overhead. The graphics driver is forced to make a lot of runtime assumptions as it can't anticipate what you'll ask it to do mid-frame. It tries really hard to maintain a functioning and correct state, which really cripples its ability to optimize GPU commands and execution. Modern graphics APIs have taken a different route from the state machines of the past, and Vulkan is no exception. All of the configuration about how we will ultimately render our pixels to the frame buffer are stored in the VK pipeline object. We switch between VK pipeline objects at runtime, but initialize and pre-configure them ahead of time, providing the driver and in turn GPU all of the information that it needs to execute our drawing commands efficiently. Providing all of this information up front means the driver gets no surprises in the middle of a rendering pass and can really choose how best to execute the given set of commands. This doesn't mean that absolutely everything has to be set in stone. Some state change is quite cheap and efficient, such as scissor and viewport changes, which we'll take a look at later on. When talking about pipelines in Vulkan, the two parts we need to concern ourselves with are the layout object and the pipeline itself. You can think of the pipeline layout as a function signature and the pipeline as the body of the function. You configure the various inputs into the pipeline using the layout, and then choose how you wish to use those inputs using various configuration options and shader modules. It's quite common to have a single pipeline layout with various different pipelines representing different materials being used in the scene. You can think of it almost like polymorphism. The function signature is the same, but the pipeline changes, and so do the various rendering configurations and shaders, yielding different results. Our first triangle doesn't require anything with regards to a pipeline layout, so it resembles a method that takes no parameters, but we'll need to create one anyways. The createGraphics pipeline function returns a VK pipeline handle, so in the future we'll add different parameters to this function, but get back VK pipelines that we'll use to represent different materials for our scenes. In order to create the pipeline layout object, we first create an instance of the VK pipeline layout create info structure. As always, set the structure type, then we set the set layout count and push constants range count fields to 0. This lets Vulkan know that this pipeline layout will not be associated with any descriptor sets or push constants, both of which are ways to get data into our shaders. Since our shaders in this introductory video are very simple, we won't be looking at adding anything here until the next video. After this, we call VkCreatePipelineLayout and pass in our VkDevice, the pointer to our pipeline layout create info structure, no allocator callback, and a pointer to the VK pipeline layout variable where we can receive the handle to our new layout object. Moving on, we can start looking at the structures that will describe the VK pipeline itself. There are quite a few of them, but they're quite simple to understand, so we can move through them more rapidly. The next block of code creates a vector of two VK pipeline shader stage create info structures, which are used to associate any shader modules we've previously compiled with the various stages of the graphics pipeline. The stage field specifies the pipeline stage we're associating a shader module with. The module field receives the VK shader module handles we just created earlier, and the pname field needs the name of the entry point function that will be executed. In this case, each shader has a main function, so this is what we're setting here for both shaders. You can also use a single VK shader module for multiple stages by using a different entry point function for the Vertex and Fragment shader stages. This can make it easier to work on your shaders as it reduces the need to bounce back and forth between different shader files, and reduces the need to duplicate code between them as well. We'll look into this in the next video. This is a good time to have our first look at the source code for the Vertex and Fragment shaders that we're using in this tutorial. These are very simple, as all we want in this lesson is to initialize Vulkan without introducing any unnecessary complexity. Overcomplicating the shaders and pipeline at this stage is a great way to run into beginner errors and have yourself scratching your head. It's best to stay absolutely as simple as possible at this phase and make sure we can get pixels on the screen before moving on to anything more complex. This is why for this lesson I've hard-coded the triangle vertices directly in the Vertex shader, which avoids the need to deal with creating vertex and index buffers and uploading the data into them. There will be plenty of that in the next lesson when we look at loading GLTF mesh data. The Vertex shader starts with the GLSL version number 4.60, which is the latest as of today, but irrelevant for what we're doing in this video. Moving on, this is the array of vertices called positions, containing the 3 vectors needed to represent our triangle. Notice the order of vertices is top, bottom left, and then bottom right, which results in a counterclockwise orientation of the vertex order. This is important, as we'll see shortly. Vulkan needs to know what vertex order describes the front faces of our geometry. I'll explain this in a minute. Next is another array of 3 vectors, this time representing 3 different colors: red, green, and blue. Here we're declaring a vector3 output variable from the vertex shader stage, which is the color we'll be assigning to any vertex that we process with the shader. Take note of the location equals 0, which dictates how this output variable maps to an input variable in the fragment shader that we'll see next. The important concept to understand is that the vertex shader deals with the individual vertices of the mesh we're rendering. The fragment shader deals with all of the fragments filling in that triangle. They're called fragments because they don't always map directly to pixel locations. We can represent subpixels, though that's not relevant for us right now. What this means though is that if we're outputting data from the vertex shader into the fragment shader, we're going from 3 pieces of data, mapping against thousands, potentially millions of fragments that represent the inner area of a given triangle. This means that the 3 colors that we're setting per vertex for our triangle need to be interpolated per fragment, depending on the fragment's position within the triangle. Your GPU is designed to do this on a massive parallel scale, so it's not a problem for it at all. We just need to make sure that we connect the wires correctly between the vertex and fragment shaders by using the same location index between the input and output variables. The main function of the vertex shader uses the internal GL vertex index variable provided to us by Vulkan to index into the vertex positions array we looked at above. As its name implies, this variable represents the index of the current vertex we're processing. When we call our draw function, which we'll look at shortly, we tell Vulkan that we want to draw 3 vertices representing our triangle, using what is called the triangle list topology, which just means that we want to draw a list of triangles, though in our case it's just a list comprised of a single triangle. What Vulkan then does is invoke our vertex shader for each vertex in our mesh, giving us a chance to transform it as needed. In order for the vertex shader to produce the final transformed output vertex, we need to write a value into another internal variable called GL position. Whatever vertex we stored there will be the output vertex position of the shader. GL position, though, is a vector with 4 elements, whereas our triangle vertices are vector 3s with 3 elements. The vertex shader output needs to be a 4-element vector, and in the next video we'll see why this is important when it comes to perspective projection, which gives our scene a 3D look. For now, let's just create a vec4 by passing our vec3 to its constructor and passing a 1 for the 4th element. With the output vertex position done, we use the same GL vertex index method to grab a color out of our colors array and pass it directly to the output color variable we discussed previously, which feeds into our fragment shader. The fragment shader is even simpler in this case. We once again see the GLSL version number at the top, followed by a couple of variables. The input vec3 is the interpolated vertex color for the current fragment invocation, which will be a blend of the 3 primary red, green, and blue colors we set per vertex previously. The input variable's location index is set to 0 to match the index of its pair, the output variable we just saw on the vertex shader with a matching 0 location. The frag color output variable is where we're writing the output color of the fragment and maps to the index of a color attachment target we will set with the same index when we issue the begin render command shortly. We once again use the vec4 constructor to wrap our interpolated vertex color and ensure that the fourth element, the color's alpha channel, is set to 1, representing a fully opaque color. Now that we've seen both shaders, let's keep moving through the create graphics pipeline method and refer back to these shaders as needed going forward. Normally when feeding our vertex shaders with mesh data, we prepare buffers and memory in VRAM that hold all of the vertices representing our mesh data. Each vertex can contain a position, a color, UV information for texturing, a normal for lighting calculations, and other details. Depending on our feature set, it's all up to us. In order for Vulkan to be able to correctly read each vertex and feed it into our shader, it normally needs information outlining what fields are a part of each vertex, their data types, and how they're laid out in memory. Since we're not concerning ourselves with vertex buffers in this introduction and have hard-coded our vertices, we get to ignore this portion of the pipeline setup. In fact, we'll be using a more modern approach when feeding the vertex shader by not asking Vulkan to push vertices into it from a buffer, but rather we'll employ a technique called vertex pulling, where we provide a pointer to the vertex buffer to the shader and directly index into it using our vertex index. Essentially, we're pulling vertices out of a buffer, rather than expecting Vulkan to push them in for us. More on this when we load GLTF models in the next video. For now, we just need to provide an empty VK pipeline vertex input state create info structure by setting its type and moving on. I mentioned previously that the pipeline will be expecting to draw using a triangle list topology, and this is where we're setting that. The pipeline needs to know how to assemble the vertices we're providing, so it's a requirement that we configure it with a topology type. There are various other topologies like triangle fans, triangle strips, points, lines, but as you've probably guessed, I won't be explaining those here needlessly. We'll take a look at them as we need them in the future. So for now, create the VK pipeline input assembly state create info structure, set its type, and the triangle list topology constant, and keep moving. We've already discussed how the depth buffer works, why it's important, and it's here that we configure it for our pipeline. To remind you, depth testing allows us to render our scenes without worrying about having to sort and draw objects from furthest to closest. We simply render the scene, and if our pipeline attempts to draw a fragment in a position where one already has been written, it ensures that the source fragment, the one we're drawing, is closer than the destination fragment, the one already in the image, before the fragment shader even executes for it. If the source fragment is further away, then it fails the depth test and is discarded, allowing us to avoid shading it needlessly and, more importantly, prevents overwriting the existing closer fragment that is already in the image. Here we create the VK pipeline depth stencil state create info instance, set the type, and configure the exact operation. First, we enable depth testing. Then we enable depth writing, which is what actually writes the depth value of each fragment into the depth buffer, allowing this whole depth testing to even occur. Then we specify the depth compare operation. What we normally want is exactly what I described. We need the source fragment's depth to be less than the existing fragments in order to pass the depth test. So we set the depth compare op field to VK compare op less to ensure that incoming fragments have a depth value that is less than any existing fragments already in the image. At the moment, we're not concerning ourselves with stencil testing or stencil effects, so we set the stencil test enable field to false, and we're done with the structure. Let's look back at the vertices that we are using to define the triangle for our lesson. The center of the screen is at 0, 0 on the x and y axes. Our top vertex is at 0 on the x-axis and negative 0.5 on the y-axis. This places it in the center of the screen horizontally and in the upper half of the screen vertically. This is because in Vulkan, the negative direction on the y-axis goes upwards. The other two vertices follow the same pattern. Negative 0.5x goes to the left and positive 0.5y goes down to the bottom half of the screen, forming our bottom left vertex, and 0.5x and 0.5y forming our bottom right vertex. We're using 0.5 here because we're specifically defining the vertices in what is called NDC, or Normalized Device Coordinates, which is a fancy way of saying that we have coordinates that go from -1 to 1 on the x and y axes and 0 to 1 on the z axis. This allows Vulkan to use coordinates that are normalized and independent from the actual dimensions or resolution of the output image. Positive 1 on the x-axis will always be the rightmost edge of the screen, regardless if we're rendering at 1080p or 4K. With this in mind, we don't normally specify coordinates in normalized device space. They end up that way after they have been transformed by our matrices. Since in this lesson though, we're only focusing on drawing the triangle, we aren't looking at matrices yet. We're simply providing our vertices as NDC coordinates in the vertex shader directly. We will see how this normally happens when we introduce a projection matrix and transform vertices with it in the next lesson. With all this in mind, in order for our image to be displayed across the actual dimensions of our screen, we need to provide Vulkan with a viewport specifying the extent of our view area. The viewport size is something that you can provide directly into the pipeline, but it's one of those rendering states that are so cheap to change that we're going to configure the pipeline to allow the viewport to change dynamically, without baking its parameters into the actual pipeline. This happens further down in the code, and we'll see it later. We still need to tell Vulkan that we intend to use a single viewport. So we set the viewport count to 1 here, but we don't need to provide a list of viewport objects here since we'll change the viewport dynamically. The scissor testing allows us to mask areas of the screen during rendering, letting us make sure that we're not rendering outside of a given rectangular area. This is used a lot when drawing UI elements such as scroll boxes or text boxes that need the text to clip at the edge of a text box. We aren't doing anything like that now, but since we're enabling dynamic scissor testing as well, we'll be providing a scissor area that matches the dimensions of our Swapchain image, encompassing the entire render area. The concept here is the same. We tell Vulkan to expect a single scissor rectangle, but we don't provide it now since it's going to be dynamic. After vertices have been processed within the pipeline, Vulkan needs to decide which parts of the screen need to be rasterized. This stage involves culling unnecessary faces and deciding which parts of a face will need to be shaded in. We create a VK pipeline rasterization state create info structure to configure the rasterizer. Here we're saying that we want the polygon mode to be fill, which means we want the entire area of our triangle to be filled in. We can also set this to a mode like line for a wireframe image, or point if we would like to visualize just the vertices. The cull mode dictates which triangle faces we'd like to ignore, or cull during rasterization. You'll recall that we ordered our triangle vertices in a counterclockwise order, and here is where we tell the pipeline that counterclockwise faces are the front faces, and that we would like to cull the back faces. This happens for performance reasons, though there are cases you need to show the back faces, such as if you're creating a see-through object, but you mostly want to avoid drawing back faces if you don't need them. Finally, I also set the line width here to 1, which isn't necessary, but if you'd like to try the wireframe mode, you should also specify a line width. If we wanted to enable a multi-sampling anti-aliasing technique for the renderer, the VK pipeline multi-sampling state create info structure is where we would configure that. Let's not worry about this yet though, and set the sample count to 1, effectively disabling multi-sampling. The next two structures are for configuring the blending operations in the pipeline. Blending is the process of mixing two colors together during rendering, and is used primarily for producing transparent objects like glass and water, but there are many other effects that can be achieved as well. This topic will get a video of its own when we look at how to handle transparent objects, but for now we just need to provide the minimal information our pipeline will need. The VK pipeline color blend attachment state structure is used to configure the color blending operations and write operations for a particular color attachment target. In our case, that's the Swapchain image we'll be rendering to. Even though we're explicitly disabling blending operations, we do need to provide a color write mask, which tells Vulkan which color bits we would like written to our Swapchain image. If, for example, we remove the R component from this mask, we would see that any color values written to our swap chain would have a 0 for their red component. We're also creating an instance of a VK pipeline color blend state create info structure where we specify that we're providing configuration for a single color output attachment and providing a pointer to the object we just filled in above. In order for us to be able to change viewport and scissor mask information dynamically, we need to explicitly tell Vulkan that we're planning to do so when we create the pipeline. We do this by filling in a structure of type VK pipeline dynamic state create info and providing a list of dynamic states that we're intending to enable. Here, we're creating a vector of VK dynamic state values and stating that we want to be able to change the viewport and scissor at runtime. Then we hand it off to the dynamic state create info structure by providing its size and data pointer. Not to be confused with dynamic state, dynamic rendering is a newer Vulkan 1.3 feature that allows us to avoid having to create render passes, subpasses, and frame buffer objects. These used to be a real pain point for beginners and a source of code bloat. Not only did they require quite a bit of boilerplate to set up, they were also difficult to understand because of some of the implicit synchronization behavior inherent to render passes and their subpasses. Dynamic rendering lets us be more explicit about resource transitions during rendering and also require far less code to use. In order for us to enable dynamic rendering, we fill in a structure object of type VK pipeline rendering create info, where we specify the number of color attachments we'll be rendering to, which is our Swapchain render target, and a pointer to a VK format array corresponding to the number of color attachments we're specifying. Since we only have a single color attachment, we're passing the address of our Swapchain color format that we saw earlier. We also need to specify the depth attachment format here as well, and we're passing the same depth format we saw earlier in the video. Well, that was a lot of structures, but hopefully this was easy to follow and understand. I know it seems like a lot of code, but this is something we're writing once for the entire renderer and we'll be expanding upon with different parameters in order to be able to create different pipelines in the future. All that's left here is to create an instance of the VK graphics pipeline create info structure and provide the addresses of all the structures we created previously. This is also a good opportunity for a quick summary. We start with the structure type as always. In order to enable a modern feature like dynamic rendering, we must pass the dynamic rendering info structure into the pnext pointer. This is a good example of Vulkan's extensibility using pnext. We set up the shader stages and associated them with the VK shader modules we compiled. We provided a blank vertex input state since our vertices are stored directly in the vertex shader. We specified our input assembly state to tell our pipeline that we need a triangle list topology. We told Vulkan that we intend to use a single viewport and scissor test, but did not specify them here statically. We configured the rasterizer to state that we want back faces culled and front faces filled in completely. We told Vulkan that we're not using multi-sampling. We're enabling depth testing and writing, but keeping the stenciling disabled for now. We configured our color blending by providing information about our single color attachment and keeping color blending disabled for now. We stated that we want the viewport and scissor states to be dynamically mutable so that we can change them during rendering. And we created a pipeline layout object that isn't expecting any push constants or descriptor sets. The last field isn't required, but I've put it here to stress the fact that we're not using render passes, which most older tutorials and videos demonstrate, but rather we're using dynamic rendering, which has to be configured using the pnext field above. And this field here needs to be initialized to null in order to create our pipeline correctly. Finally, we can call the VkCreateGraphicsPipeline function, passing our VkDevice, null pointer for the pipeline cache, which will come in handy in the future, the number of pipeline create info structures we're passing, which is 1, and the pointer to the VK pipeline info structure above. As always, null pointer for the allocator callback, and finally the address of a VK pipeline variable where we're going to receive our new shiny VK pipeline handle. We also make sure that everything executed okay and return our new pipeline handle from this function where we can receive it in the calling code. Traditional rendering APIs allow you to send work to the GPU and immediately start executing the commands. That's why they're called immediate mode APIs. This can be easier to work with, but it forces us to rely on the graphics driver to handle CPU and GPU synchronization. And as we already know, the driver can't possibly optimize for every scenario, so it leaves a lot of performance on the table. Vulkan, for the most part, doesn't perform any synchronization for us, so the CPU and GPU will run completely independently. So it's up to us to ensure that we introduce the necessary synchronization in order to avoid corrupting memory during rendering. Vulkan provides us with the tools we need to make this happen, though it can be tricky and a lot of beginners get tripped up and frustrated precisely here. A naive renderer flow could look something like this. The CPU prepares the data for a frame it wants rendered and submits the work to the GPU, waits for it to complete, and then sends off the image to be presented. Once this process completes, the CPU once again begins preparing the next frame, and the process continues indefinitely. As you might have guessed though, this creates stalls in the renderer where the CPU and GPU are idly waiting on each other, wasting precious time that could be spent doing actual work. It would be much better for us to have the CPU prepare a frame, submit it to the GPU for rendering and presentation, then immediately begin preparing the next frame's data and draw commands. If done correctly, this results in much smoother and more responsive games. The key thing to remember is that memory that the GPU is using at any given time should not be written to by the CPU while it's preparing for the next frame. So how do we achieve concurrency then? What we do is ensure that the data that must be read or written to concurrently by both sides should be replicated a number of times. This means that if the GPU is reading from a set of data for frame 1, the CPU can be busy preparing the data for frame 2 in a completely different block of memory. For example, if a shader is reading a matrix or a vector in order to draw an object at a given position during frame 1, the CPU must only be allowed to change a separate copy of that object's data while it prepares to submit frame 2. This is called having multiple frames in flight. What we need to do is take all of our CPU-GPU shared objects and create multiple copies of them. In this lesson, we have a struct called frame resources, which contains fields for any shared resource. Then we create a frame resources instance per frame in flight. If we wanted to have the CPU be able to work on up to 3 frames while the GPU is busy rendering, then we'll have 3 instances of the frame resources struct. A common point of confusion here is the frames in flight number and the number of Swapchain images. I've seen this confused even amongst prominent tutorials. These are independent concepts and aren't tied to one another. The Swapchain images are just the canvases that the OS lends us to draw on before we hand them back for presentation, and we rotate through them frame over frame. The frames in flight are just multiple copies of our data so that the CPU and GPU don't step on each other's toes while working. With that said though, we should make sure that the minimum number of Swapchain images matches our number of frames in flight. So if we wanted 3 frames in flight, then we should have at least 3 Swapchain images. As long as a frame in flight can ask for an available image and is able to acquire one quickly, then things can run smoothly. If we only have 2 Swapchain images and say 4 frames in flight, then you could see how you could potentially end up waiting for the presentation engine to finish displaying one on screen before it can free it and hand it back to you to draw on it again, creating a bottleneck. We're going to drill down into this even more during rendering, so let's push on. Moving into the create sync resources method, let's have a look at what we'll need in order to allow the CPU and GPU to work concurrently like I described previously. In this tutorial, we'll be using a more modern feature of Vulkan called timeline semaphores in order to achieve the frame over frame synchronization. But it's important to also understand how this has been done with Vulkan traditionally, as many tutorials and examples haven't caught up, and it'll also give you a better understanding and appreciation of the problems the timeline semaphores solve. Synchronization between the CPU and GPU has in the past been done with the use of fences, represented by the VkFence objects. Fences are used when you want the CPU to wait on operations to complete by the GPU before proceeding. Signaling a fence on the GPU unblocks the waiting CPU, allowing it to continue working on data that was previously in use by the GPU. Assume we have a renderer with up to 2 frames in flight. We would create 2 resource blocks in our renderer, allowing the CPU to record up to 2 frames before stalling and waiting for the GPU. Along with each resource block, we also create an associated VkFence object, which is used for protecting each resource block from an overwrite if it's currently in use by the GPU. As we discussed, it's critical that we don't write over resources for a particular frame while the GPU could be busy reading from those same resources. We begin by rendering frames 1 and 2, neither of which need to worry about overwriting any in-use resources, since nothing is obviously using those resources yet. Frame 1 uses resource block 1 and frame 2 uses resource block 2. The 2 frames can be recorded and submitted to the GPU as quickly as possible since our renderer can record up to 2 frames in flight. Frame 3 needs to wait for the resources from frame 1 to become available again in order to overwrite them. Once the GPU has completed rendering frame 1, it signals the fence associated with the resource block, letting the CPU know that it has finished reading from those resources. The CPU can then begin preparing frame 3's data by reusing resource block 1. Frame 3 is recorded and submitted to the GPU, and frame 4 can begin using the same process and utilizing resource block 2. The renderer can then continue producing frames 5, 6, 7, 8, and so on by alternating between the 2 blocks of resources available for the 2 possible frames in flight. One thing to note is that if a VkFence is being used for the first time, such as in frames 1 and 2 in our example, we wouldn't want the CPU to sit there and wait forever for a fence to be signaled that has never actually been submitted to the GPU with any work. This is why fence objects must be initialized to the signaled state so that when the CPU tries to wait for them for the first time, they're already signaled and it can proceed. So fences are used for synchronizing the CPU with the GPU, but sometimes you also need to synchronize the GPU with itself across multiple queues. In these cases, you would use a binary semaphore to perform the synchronization. And you could end up with quite a few semaphore objects, making things messy and error-prone if you have to synchronize multiple times. We won't look at GPU to GPU synchronization for now, but I'm simply mentioning this to state that a single timeline semaphore can be used to replace the aforementioned fences and any semaphores used for GPU to GPU synchronization. Okay, but what's a timeline semaphore? A regular binary semaphore can only be in an unsignaled and signaled state. A timeline semaphore represents a monotonically increasing 64-bit integer. Put simply, this just means that a timeline semaphore value never decreases. It can plateau and stay the same or increase, but it never gets smaller. Now, instead of having the CPU wait on a fence to be signaled by the GPU for a given frame, we can simply wait for a single timeline semaphore to reach a certain value instead, which gets set by the GPU when a batch of submitted commands are completed. And since semaphores can also be used for GPU to GPU synchronization, we can use that same timeline semaphore object to synchronize work between GPU queues. All you need to know for now is that we create a single timeline semaphore to synchronize our frames in flight. When we look at the render method shortly, the purpose and usage of the timeline semaphore will become much more clear. We first create an instance of a VK semaphore type create info structure, set its S-type field, and set the semaphore type field to VK semaphore type timeline. And then we specified the initial integer value of the semaphore, which we're setting to 2. Next, we need a VK semaphore create info structure. We set its type and use the pNext field to pass the address of our semaphore type info object. Once again, we see the pNext field being used in order to utilize newer Vulkan functionality that wasn't available in the initial specification. When Vulkan sees that we're passing a semaphore type structure in the pNext field, it will look at the semaphore type field and create our timeline semaphore, instead of creating the usual binary semaphore. With those two structures set up, we can call VkCreateSemaphore, passing in the VkDevice, the address of our semaphore info struct, null allocator callback, and the address of a VK semaphore field in the class instance that will receive the new timeline semaphore. If all goes well, we can move on to the next section. Despite how useful timeline semaphores are, there's one thing that they can't synchronize for us, and that's our interactions with the presentation engine. Before we can draw anything each frame, we need to make sure that we have something to draw to. Of course, I'm talking about one of the Swapchain images. The issue is that we don't choose which image to draw on, but rather ask the presentation engine for one each frame. This process is asynchronous, so we don't just immediately get a ready-made image right when we ask for it. What we do get is the index of the image that we're going to draw on, allowing us to prepare our draw operations accordingly. The signal from the presentation engine that the image at the given index is ready to be rendered on may happen after we've already sent the commands to the GPU, so we need a way to block our draw commands from executing on the GPU until the presentation engine has given us the go-ahead. This is done with a binary semaphore. We simply create a binary semaphore for each of our frames in flight, pass it along when we ask to acquire an image, submit our draw commands, and then the semaphore is signaled by the presentation engine, letting us know that we can begin rendering to the Swapchain image. The GPU executes the submitted commands and signals our render complete semaphore when the commands have all been executed. We then submit the Swapchain image for presentation along with that same render complete semaphore so that the presentation engine can have something to wait on. Once that semaphore is signaled by the GPU, the presentation engine knows we're done rendering and that the image can be displayed on screen. Here we iterate over our frames and flight objects and create the binary semaphores just like we did previously. At this point, we're almost ready to start rendering, but in order to get our draw commands to the GPU, we need to discuss one more final thing as part of the Vulkan initialization, and that's the command buffers. I mentioned earlier that older graphics APIs functioned as large state machines. You change a state, submit a few draw commands, change another state, submit some more commands. As simple as that sounds from a programming perspective, it doesn't map well to how GPUs actually operate and execute instructions in the queues. What our hardware and driver really wants is for us to prepare everything up front. This is why we create our graphics pipelines up front, and also why we're going to record commands up front. When we prepare the commands ahead of time and submit them once in bulk, we gain a number of things. We decouple the command recording from the GPU submission, which means that we can submit all the commands in bulk once in the frame. And the GPU knows everything up front, allowing it to prioritize and optimize. This approach is also much better for creating multi-threaded renderers. Each thread could record commands independently into its own buffers and synchronize with the other threads only during submission. Game programmers have been doing this for many years by implementing their own commands and command buffer structures, though the older graphics APIs still required commands to be submitted one by one, which means if you have 100 draw commands, you have to do 100 calls into the graphics driver. Nowadays, Vulkan and the rest of the modern graphics APIs have this functionality built in first class, allowing us to record as many commands as we want and then submit them in a single shot. In order to record commands in Vulkan, we need what is called a command buffer. And to be able to store those commands, each command buffer needs to be linked with a command pool, which is a memory pool of commands in order to reduce runtime memory allocations. With our multi-frame in flight setup, we create a command buffer per frame in flight. This way, when we submit one command buffer for processing on the GPU, we can start recording immediately into another command buffer for the next frame. We're also creating a command pool per command buffer. This way, each command buffer has its own memory. At the start of each frame, all we have to do is reset the command pool in order to be able to reuse its memory and record again for that next frame. Taking a look at the create command buffers method, our work is pretty simple. We iterate over our frames and flight structures once again and create a command pool and command buffer for each one. Creating the command pool is simple. We create an instance of the vk command pool create info structure. The important thing though is that we need to specify the queue family index we're associating with the command pool. We can only submit commands using this pool to queues that share the same family index. Different queue families have different hardware requirements, so you cannot record commands requiring one queue family into a command pool that has been created for a different queue family. To create the pool, we call VkCreateCommandPool, pass our device, the address of the pool info structure, no callback, and the address of the VK command pool object in the current frame resources object. If the pool is created successfully, we can move to allocating the command buffer. For this, we need an instance of the VK command buffer allocate info structure. Here, we can specify the command pool we just created for this command buffer, and the commands we record into this buffer will be created using it. When we reset or destroy the command pool, this command buffer will also be reset or destroyed. We also need to specify the type of the command buffer we want. This can be either a primary or secondary command buffer. In short, primary command buffers are those that we submit directly to queues, and secondary command buffers can be submitted into a primary command buffer, allowing a sort of hierarchy of submissions. Lastly, we specify the number of command buffers we wish to create right now. Since we only have a single command buffer per frame in flight, we can just specify one here. To allocate the command buffer, we call VkAllocate command buffers with our device, allocate info structure, and where to receive the VK command buffer object. As I showed previously, we'll be storing the command buffers inside instances of the frame resources struct. With that done, before we draw our triangle, let's take a short detour to our shutdown method and make sure we're cleaning things up properly. The last time we looked at this method, we had added code to clean up the VMA allocator memory. Since then, we've added a number of objects into our renderer that need to be destroyed when we shut down the application. Before we start deleting objects though, we're going to flush the GPU. All this means is that we're waiting for any pending work to finish executing before we start cleaning up. This is done with a simple call to VkDevice wait idle and passing our device handle to it. This is a very heavy-handed synchronization method and should generally never be used in your runtime code. Since we're only doing this during the shutdown, it's perfectly okay. Once we're sure the GPU has done its work, we can call the various cleanup methods. This code is quite self-explanatory, so I'm not going to dwell too long on things. First, we'll destroy the timeline semaphore. Then we iterate over all of the frame resources objects and destroy the image acquired semaphores as well as the command pools. We don't need to destroy the command buffers themselves as they're allocated using the command pools. Next, we'll destroy the pipeline layout, followed by the pipeline. Then we'll destroy the shader modules that were used by the pipeline. Finally, we'll add a call to our destroy swapchain method to clean up any swapchain related resources. We looked at this method in the swapchain section of the video and how we're also using it when we recreate the swapchain. And with that, we're done with the cleanup code. Just remember to call this shutdown method at the end of your application to actually clean things up. Now it's time to move on to the main event, which is our rendering code. Let's take a look. At this point, we've discussed all of the pieces we'll be using in our application, such as the swapchain, the synchronization objects, the command buffers, and it's here that we actually put them to use. The first block here isn't related to our rendering code, but it should happen at the start of every frame. We're checking a boolean that flags if the Swapchain recreation is needed. This value gets set to true further down in the case that the swapchain has become invalid. If we need to recreate the swapchain, we first need to destroy any swapchain and depth buffer resources currently in use, then recreate them. Since they may actually currently be in use though, we can't just pull the rug out from under the GPU's feet, we need to give it a little time to finish whatever it's doing. Then we can destroy the swapchain. Once again, we see the VkDevice wait idle function, which lets us wait for the GPU to finish doing what it's doing before we recreate the swapchain. We're introducing a major stall here and saying that the CPU will simply sit here and wait until the GPU is done executing every submitted command. This is another one of those instances where it's okay to use this function because it's not actually being used to synchronize rendering. Window resizing and Swapchain Recreation are exceptional scenarios and not part of the rendering hop path. Since we're using a timeline semaphore to keep our frames in flight and out of each other's resources, at the start of each frame, we need to generate a few values that will help identify which resources we're using, what timeline value we'll wait on, and what timeline value will signal for this particular frame. By taking the current frame's index and using the modulo operator with the max frames in flight number, we can get the current frame's resource index. When discussing all of this, please remember that our maximum frames in flight is 2. Doing this operation gives us a value alternating between 0 and 1, which acts as the index into our frame resources array. Next, we compute the value that the current frame will set the timeline semaphore to when it completes. When a future frame tries to reuse the current frame's resources 2 frames from now, this will be the value that it will wait on to ensure that the resources have become available. With that in mind, the wait value is the value that the current frame will wait on before it begins using the resources. We're taking the current frame signal value and simply subtracting our max frames in flight value, which again is 2, ensuring that the current frame waits for the signal from 2 frames ago in order to proceed. You'll recall how we use the timeline semaphore to restrict access to frame resources if the previous frame using those resources is still in flight on the GPU. The new timeline value is set at the end of each frame by the GPU after all commands have finished processing, letting the waiting frame know that the resources can be reused once again. To introduce the wait and ensure we're not starting to write over data that may still be in use, we use the VkWaitSemaphores function. In order to call it, we need to create an instance of the VkSemaphore info structure, where we specify the number of semaphores we need to wait on, which in our current case is just 1. The p_semaphores receives the address of a list of semaphores, which in our case is just a single timeline semaphore address. The p_values is a list of wait values we wish to wait on, matching each semaphore in the semaphores list respectively. Since we're only waiting on our timeline semaphore, we just pass the address of the wait value we computed above. We can then call VkWaitSemaphores and pass our device, the address of our semaphore wait structure, and the timeout value for the wait period, which we'll just set to a very large integer for now. This call forces the CPU to sit there and wait for the timeline to reach the value we provided. Upon that value, the CPU would unblock and allow it to continue executing this code. You may already be asking this question though, what happens during the first 2 frames? Why are they waiting on any signals if there is nothing preceding them? You might think that we should wrap this wait call in an if block, ensuring it only executes for frames 3, 4, and so on, since they will actually have something to wait on. Adding this if block though would introduce a branch on the render hot path, which is only relevant for the first 2 frames, which is ridiculous considering our application will likely render hundreds of frames per second. To understand how we get around this, consider what the initial values are for our timeline semaphore and the signal and wait values for each frame. The timeline semaphore starts with a value of 2, based on the maximum frames in flight. The next signal value variable starts with a value of max frames in flight plus 1, which means frames 1 and 2 have signal values of 3 and 4. The wait values for frames 1 and 2 are computed by subtracting the max frames in flight number from the frame signal values, so frames 1 and 2 wait on values 1 and 2. And of course, since we set the initial value of the timeline semaphore to a value of 2, the first 2 frames don't actually have to wait on anything since they wait on values 1 and 2. They just start executing immediately. Once frame 3 comes along, its signal value will be 5 and its wait value will be 3. We know that frame 3 will want to use the resources from frame 1, so it will wait for the timeline semaphore to hold the value of 3 before starting. And as I just showed, frame 1 will set the timeline semaphore to that value upon completing. Frame 4 will signal a value of 6 and wait on a value of 4, matching the signal value of frame 2. Be sure to rewind and work this out on paper if you need to. It can be a little confusing at first. Make sure you wrap your head around this whole process though, because this is the tripping point for many beginners. After the call to VkWaitSemaphores completes, we know it's safe to start working on the current frame. We can begin by grabbing the current frame resources object using the index we computed above. Once we have that, we can reset the command pool so that we can reuse its memory and record a fresh set of commands for this current frame. We provide our device, the current command pool we're resetting, and a value of 0 for the flags parameter. Now that we know which resources we can work with, we can proceed in asking for a Swapchain image to draw on. We'll need the binary ImageReady semaphore, which we're storing inside of our frame resources object. We can grab it out of there, then call VkAcquireNextImageKHR to ask for a Swapchain image. The parameters are the current device, the Swapchain we're working with, a timeout value for the wait, which will once again set to a large integer, the binary semaphore to be signaled when the image is ready to be drawn on, and we'll pass null for the fence parameter as we're not using that. Finally, just the address of an integer that will receive the swapchain image index. This function will likely return quickly and give us the index of the next image available for us, which means that the OS compositor is finished with the image. This does not mean that the GPU itself is done displaying it. This is where the semaphore comes in. It will be signaled once the GPU is finished with the image, telling us we can once again start rendering onto it. The actual return value of this function is VkSuccess if everything is okay with the image and we're drawing as normal. There may be exception instances though where the swapchain images are no longer valid for one reason or another, and the swapchain needs to be recreated. If the return value is VkErrorOutOfDate KHR, then the swapchain images can no longer be used at all and we need to immediately recreate the swapchain. In this case, we set the swapchain recreate flag to true and exit out of the method immediately. As you saw previously, this flag is checked at the start of this method and the swapchain is recreated as required. If the acquire result code is vk suboptimal KHR, this means that the swapchain is still usable, but we should recreate it as soon as possible to avoid performance and graphical issues. This is the result code you would get when you resize the window, which would lead to a draw surface that no longer matches the swapchain dimensions. In this case, we'll flag that we want the swapchain recreated at the start of the next frame, but we'll continue rendering this one as usual. We're ready to start recording commands in this frame's command buffer, so we'll tell Vulkan that we'd like to begin that process by calling VkBegin command buffer. It takes the current frame's command buffer, as well as the address of a vk command buffer begin info instance, which we'll use to tell Vulkan that the command buffer will only be submitted to the queue a single time, before needing to be reset. You'll recall that the command pool reset you saw at the start of the frame also resets the command buffer. When working with modern graphics APIs, care must be taken to ensure that the various resources used throughout the pipeline are in the correct memory layout depending on the use case. This means that the bits and bytes of an image, for example, are laid out one way when they are rendered to, and a different way when they're being presented to the screen. Before talking more about layouts and their transitions, let's quickly talk about what barriers are. But before we talk about what barriers are, let's make sure that we have a general idea of what the Vulkan pipeline is. And no, I'm not talking about the VK pipeline object we created earlier, but rather the high-level flow that your geometry goes through when you submit something to be rendered. The various stages your vertices go through, from input assembly, through your shaders, onto rasterization, where the geometry turns into actual pixels, and finally into blending, where your pixels, or fragments, are blended into the existing image. Some of these boxes will be familiar as we configured those stages when we created our graphics pipeline. We don't need to study the entire pipeline at the moment, as we'll discover and learn more about it as we implement more features. For this video, we only really care about the Vertex and Fragment shader stages. When we tell Vulkan to draw our triangle, our current application jumps into the Vertex shader where our vertices are hard-coded, and then they make it through rasterization, where Vulkan decides which part of the screen needs to be filled with color, then through our Fragment shader where the colors are written into our swapchain image. You'll also recall that we have a depth image that we created and enabled depth testing in the pipeline. So we need to quickly mention the early and late fragment test stages. The early fragment test stage is able to look at a given fragment that needs to be shaded and decide whether it needs to be shaded at all. As you may have guessed, this would be where the depth testing initially occurs. If a given fragment is behind an existing fragment that has already been drawn, then the early fragment test will simply discard this and avoid running the fragment shader needlessly. If for some reason you decide to change the depth value of a fragment in your fragment shader, Vulkan will know this and be forced to always run the fragment shader, since the early test wouldn't be able to decide if a fragment should be discarded, given that its depth changes after the early fragment test occurs. In this case, the late fragment test would run and make that decision prior to blending your final output color into the image. With Vulkan, we get explicit control about how commands flow through the pipeline we just looked at. We can create dependencies where we block certain commands from executing until previous commands have reached a specific point in the pipeline. This is done through the use of barriers, which let us specify a source and destination pipeline stage for the barrier. The source stage specifies the Vulkan pipeline stage we need existing commands to reach before allowing any subsequent commands to reach the destination stage. Essentially, we can say that we need all existing commands to reach a specific point in the pipeline before we move on to a later stage. This control can be fine-grained even further by specifying the type of access we want to block at the source and destination stages. For example, we may only want to block writes during a particular stage and not worry about commands requiring a read operation. Along with the barriers, we can perform transitions on the memory layouts of particular resources. Like I mentioned earlier, it's important for resources like our swapchain and depth images to be in specific memory layouts depending on how they will be used during a given stage. The layout transitions are performed during the barriers, as the barriers themselves protect the resource from being used in particular ways until the transition has taken place. In the current block of code, we're stating that we'd like to create a barrier where any writes into the color attachment, that being the swapchain image, are blocked until the swapchain image specified here has been transitioned into the VK image layout color attachment optimal. This layout type is what the hardware prefers when it needs to write fragments into the swapchain image. The source stage mask here states that we're creating the barrier at the point when color attachment output happens in the pipeline, and a source access mask of 0 dictates that we don't care about which operations we're blocking. This will include reads and writes. The old layout of the image is set to undefined, which means that we don't know, nor do we care what the previous layout was. We just need the image to be transitioned into the requested new layout. Once the transition is complete, writes to the image will be allowed to continue, and the swapchain image can be populated with our fragment data. We can further control which part of the image we want to transition using the sub-resource range field. In our case, we're transitioning our swapchain color image, so we set the aspect mask to VK image aspect color bit. The base MIP level is set to 0 and the MIP count is set to 1, since this is a swapchain image and it doesn't get sampled at various MIP levels. The same goes for the image array details. We have only a single image element here, so we set the base array layer to 0 and the layer count to 1. You'll notice that this barrier object is created into a vector. This is because we have another barrier and transition that we want to perform before we can start rendering. Just like we need to ensure that the swapchain is in the correct memory layout for output, we need to ensure that the depth image is also appropriately transitioned. With this, we're telling Vulkan to place a barrier which ensures that previous commands have completed the early fragment test stage, and the depth image we specify here has been transitioned into the depth attachment optimal layout. This is because any writes into our depth image during the early and late fragment stages will require the image to be in this layout for optimal performance. The sub-resource range is similar to the swapchain image, with the exception that we're setting our aspect mask to VK image aspect depth bit. With the VK image barrier 2 objects now sitting in the vector, we can fill out a structure of type VK dependency info, where we specify the number of barriers we wish to create and provide a pointer to the memory containing the barriers themselves that we just defined. Then it's just a matter of calling VK command pipeline barrier 2, passing the command buffer, and the address to the dependency info struct object above. The barriers will be recorded into the command buffer, and when the GPU executes our commands later, any commands recorded prior to this point must complete the stage and access specified by the source mask fields. Commands after this call must wait at the stages and access specified in the destination mask fields. In this lesson, we're using a newer feature of Vulkan called dynamic rendering. Dynamic rendering is a more explicit and streamlined way of doing rendering compared to the traditional render passes and subpasses that Vulkan offers. Render passes are a much heavier feature that require frame buffers, the configuration of attachments, subpass dependencies, layout transitions, and implicit barriers. The newer dynamic rendering approach is much more explicit and easier to follow since we explicitly perform our barriers, layout transitions, and everything else. Render passes are a bit of a black box that you configure and hope you got it right, making debugging quite a bit more difficult. The benefits of traditional render passes have been that they allow you to set up subpasses, which can take advantage of tile-based and mobile GPUs much more efficiently, allowing us to perform more complex render operations while keeping our working data in fast GPU cache memory. This is something dynamic rendering lacked until recently. the VkKHR dynamic rendering local read extension was added, allowing us to take full advantage of these advanced GPU features using dynamic rendering. We'll look at this in a lot more detail when we implement the deferred renderer into the application. Vulkan's dynamic rendering no longer requires frame buffer objects, but you still need to tell Vulkan about your render targets. To do this, we need to create a couple of instances of the VK rendering attachment info structure, one to describe our Swapchain color output target, and another for the depth target. Looking at the Swapchain image target details, here we'll configure how Vulkan should treat our Swapchain image during rendering. We specified the image view that we'd like to use as the render target. Since we created our image view objects when we created the Swapchain, we can just use our Swapchain image index to grab the corresponding image view for the current image index. We're also telling Vulkan what layout to expect our color attachment image to be in when we start rendering. The load op field specifies what we want Vulkan to do with any existing data that's currently on the image when rendering starts. Since we're starting a new frame, we want Vulkan to just clear whatever is currently in the image using the clear color specified in the clear value field. The store op states what we want to happen to the data at the end of the dynamic rendering pass. We obviously want to keep that data so that we can present it on screen, so we specify vk attachment store op store. For the depth buffer attachment, we specify our depth image view as the attachment target. The image layout should be vk image layout depth attachment optimal, just like what was specified in our barrier to transition the image. The load operation is once again clear, even though we're not working with stencil data yet. The depth buffer needs to be initialized to a value of 1, which is the furthest value a fragment can have. During rendering, the z-coordinates are normalized to be in a range from 0 to 1. If we cleared the depth buffer with a value of 0, none of our fragments that we're rendering would pass the depth test since the existing value in the image is 0, which is already the closest a fragment can be. This would result in nothing being written to our output targets, and we would just get a blank image. For the store operation, we don't need the depth data beyond this frame, as we're not displaying it anywhere or reading from it. So we tell Vulkan that we don't care what happens to this data, and the hardware can discard it if it needs to. With the attachments described, we can tell Vulkan to begin rendering. To do this, we create an object of type VkRenderingInfo, which provides the high-level details for the dynamic render pass. The render area field defines the limits of our render operation. Think of it as an absolute canvas size for the renderer. We want to use the entire Swapchain image here, so we specify 0 for the x and y coordinates, and the Swapchain dimensions for the width and height. The layer count specifies the number of image array layers we'd like to render to. This would be useful for various advanced techniques, but since we're rendering directly to our Swapchain, we simply specify a value of 1 here. Here we're specifying that we have a single color attachment target, that being the Swapchain image. The pColor attachments field receives the address of the color attachment object we just created. There may be cases where you have multiple color attachments, like if you were building a deferred renderer and had to store more than just color data during the first render pass. The pDepth attachment field stores the address of the depth attachment object we created above. With that structure created, now we can call the vk command begin rendering function, providing our command buffer and the address of the rendering info object. The start of the dynamic rendering pass will be recorded in the command buffer, and from here on, we can perform any of the draw operations we'd like for the current frame. When we created the graphics pipeline, we stated that we would like to be able to set the viewport and scissor areas dynamically during rendering. It's here that we can do that. The viewport area allows us to specify the area of the screen that we'll be rendering into, which will also dictate the extent of the normalized device coordinates. This is different from the render area we specified above, as the viewport is more of a mathematical concept that dictates how vertices will be processed in the pipeline. To set the viewport, we create a VK viewport object, specifying the x and y position of the top left corner of the viewport, as well as a width and height value for its extent. Calling vk command set viewport during our dynamic render pass is what will actually set the viewport. For this, we pass in our command buffer, we specify the index of the first viewport object, also the total number of viewport objects, and the address of the list or single viewport object that we're providing. The scissor test allows the renderer to completely discard areas of the screen outside of a given rectangle. Normally, this is how you render things like text boxes or scroll widgets, where the content of the user control needs to be able to scroll along the screen, but only have a portion of itself visible to the user. For our purposes, we're setting the extent to the entire Swapchain image, as we don't need to perform any specific scissor tests yet. To set the scissor area, we call VkScissor, passing our command buffer, the index of the first scissor, the number of scissors, and the address of our scissor object. We finally reached the holy grail of all aspiring Vulkan developers, our first draw call. In order for Vulkan to know how to draw our vertices, we need to tell it to use our graphics pipeline. We do that with a call to VkCommandBindPipeline. This function takes in our command buffer, as well as an argument specifying where we wish to bind the pipeline. Since we're using a graphics pipeline, we need to set the bind point to graphics, ensuring that the correct hardware is used for our pipeline. The last parameter is where we specify the actual VK pipeline handle, which we got when we created the pipeline earlier. Now with the pipeline bound, we can tell Vulkan to draw some vertices. Calling VkCommandDraw is how we do that. We specify the command buffer, as well as the number of vertices we want to draw, followed by the number of instances. At the moment, we're only drawing a single triangle at the center of the screen. The last two parameters specify the vertex and instance indices that we want to start at, which we don't care about right now and we'll leave at 0. Since our bound pipeline expects a list of triangles to be supplied, Vulkan will take the 3 vertices and rasterize a triangle for us using the settings we configured into the pipeline. To finalize the render pass, we call VkCommandEndRendering and provide the command buffer. At this point, we're telling Vulkan that we're done with drawing for this current frame. So now our command buffer contains our rendering commands, and after the GPU processes them, we'll have a picture of a triangle on the Swapchain image. In order to display this image though, the Swapchain needs to be in a different memory layout. So you guessed it, we need another barrier. With this barrier, we're stating that all writes to the color attachment need to complete, but since we're not blocking some specific stage in the pipeline from continuing, our destination stage is simply set to none, with an access mask of 0. What the barrier will do is wait on all writes to the Swapchain image to complete before performing the layout transition. The layouts should start to make sense now. We previously transitioned the Swapchain image to a color attachment optimal layout in order to write to it. Now we'll be sending the image for presentation, so we want to change its layout to one suitable for presentation. The VK image layout present source KHR is what we want. Once again, we need to specify the Swapchain image so the barrier knows what image to transition, and the sub-resource range is just like before. Creating this barrier is nothing new for us now. We just need to create the dependency info object and then call VkCommandPipelineBarrier2. At this point, the command queue will have a barrier that will ensure all color output commands are complete before transitioning the image for presentation. Now that we've recorded the commands required to render the triangle, we need to submit our recorded commands to the GPU so they can actually be executed. Before a command buffer can be submitted to a queue, it needs to be ended, and this is done with a simple call to VK and command buffer, along with the command buffer handle. Now it's time to move on to submitting the command buffer to the queue. We've already discussed why it's important to synchronize our drawing commands with the presentation engine, which is what actually displays the image on screen. In short, we need to ensure the Swapchain image is ready for use before any color output can happen. We previously created a binary semaphore that the presentation engine can use to signal to the GPU when we can start actually writing to the image. We handed the semaphore to the presentation engine when we called VkAcquireNextImage KHR, and it will signal it when ready. Now we need to ensure that the GPU blocks output to that image until the semaphore is signaled. We do this by passing the ImageReadySemaphore along with our queue submission. First, we need a VkSemaphore object, which specifies what semaphore to wait on and what stage of the pipeline needs to be blocked until that semaphore is signaled. Since we don't want any writing to the Swapchain image, we set the VkPipeline stage to color attachment output bit here. That handles what to wait on, but we also need to emit a couple of signals at the end of the frame's execution on the GPU. At the end of the frame, the image is going to be handed off to the presentation engine for presentation. The presentation engine will use the render completion binary semaphore as the signal to wait on before trying to display the image. and it will receive that signal when all graphics commands have finished executing. Once the semaphore is signaled, the ownership of the image is transferred back to the presentation engine and the image is out of our hands. As you'll recall, if the CPU is waiting on this frame's completion in order to reuse its resources, like the command buffer and pool, the timeline semaphore needs to be updated the moment the GPU execution for this frame is complete. We simply tell Vulkan to signal the timeline semaphore and provide the signal value we calculated at the start of the frame. The waiting frame on the CPU will see that the timeline's value has changed, and recording will proceed in the associated frame in flight. In order to submit the command buffer to the queue, we need to create a couple of structures, of course. First, we create a vk command buffer submit info object, where we simply specify the command buffer that we're sending to the queue. Next, we create a vk submit info to object, and here we specify the number of semaphores that need to be waited on. In our case, that's just the image acquired semaphore, followed by the number of command buffers we're submitting, which is just the single command buffer we specified above. Then, followed by the number of semaphores we're going to signal, along with the data pointer provided by the vector of signal semaphores we just created. Calling vkQSubmit2 is how we finally submit everything. This call requires the handle of the graphics queue we created during initialization, the number of submissions we're making, along with the address to those submission objects. Also, there's an optional fence that could be signaled when all execution is complete. Since we're using a timeline semaphore, we don't need this fence and we can simply pass a null here. With our commands now submitted to the GPU, we can tell the presentation engine to display the image. Of course, the image won't be immediately displayed, as we have our trusty render complete semaphore that will be signaled once all rendering is complete. Create an instance of the VkPresentInfo structure where you specify the number of semaphores to wait on before presenting the image, followed by the single render complete semaphore that we would like to actually wait on. Next, we specify the number of swap chains we're using, which is just 1, and the address of the swap chain itself, followed by the address of the image index, which we got at the start of the frame. We can also provide a list of VkResult variables to be filled with results of each Swapchain presentation, but we don't need that and we can just pass a null. Finally, call VkQPresentKHR along with the graphics queue we would like to use and the address of the PresentInfo object. This will request the Swapchain image to be presented, but only after the GPU commands have finished executing, as signaled by the render complete semaphore. And that's all there is to it. No, but seriously, I know this was a lot of code, but think about it. You now have a solid foundation to build your Vulkan renderer. I hope I managed to explain the concepts and API in a way that's easy to understand while being respectful of your time. I'm very interested in hearing what you plan on making with your newfound Vulkan powers. Please let me know down in the comments. If you appreciate content like this and the effort that goes into it, please consider supporting the channel using my Ko-fi link, or simply just being a subscriber. Thank you for watching, and watch out for the next video.